Well, good afternoon, good morning, or good evening, depending upon where you are in the world, and welcome to today's DevOps.com webinar. I'm Charlene O'Hanlon, moderator for today's event, and I welcome you. We have a great webinar on tap with some really interesting information, but before we get started, we do have a few housekeeping items we need to go over. First of all, today's event is being recorded, so if you miss any or all of the event, you will be able to listen to it on demand. We'll be sending out an email following today's presentation that includes a link to access the webinar on demand. And we are taking questions from the audience. So if at any time during our presentation you have a question for our panelists, please don't wait, don't hesitate. Just use your GoToWebinar control panel and submit your questions. And we'll take a few minutes near the end of the presentation and go through those questions. Okay, with that, we'll go ahead and kick off today's webinar, which is why DevOps needs to embrace distributed tracing. Our speaker today is Spoons, Daniel Spoonhour, who's the CTO at Lightstep. Hey, Spoons, how are you?
Great, thanks.
Great. Well, thanks for joining me, and I'm going to put myself on mute and let you get right to your presentation.
Great, thank you. Yeah, hey everybody, glad you could join today. I'm Spoons, or as some people know me, Daniel Spoonhour, and I'm the CTO and one of the co-founders at Lightstep. At Lightstep, we build tools to help developers, operators, and DevOps engineers build, deploy, and maintain systems with confidence and at scale. And I am going to show a few screenshots from Lightstep today, mostly because I wanted to use real examples of data that I know from the real world. And in one case, because it's sort of the best way, I think, to explain what distributed tracing can do. If you want to see more, you're welcome to go to lightstep.com, where you can start using Lightstep tracing today. Okay, so with that, before I get into distributed tracing, before I actually get into code, I kind of wanted to talk about all of you for a minute. You know, you, the service owners, you, the DevOps engineers, the SRE. And just think a minute, what's your day like? Who do you talk to? Who's the first person that you Slack when you get into work? Maybe who don't you talk to? Which team do you, wonder about what they're up to, or worry about what they're up to? And that's, really about the way we organize ourselves in some ways. So, and not just ourselves, but our code. Maybe you thought that was an org chart, and I guess it could be, but it's also the way that we organize our software, whether that's statically in terms of the code itself or how we deploy it. And this is all kind of, as part of something that you may have heard of, something that Gene Conway wrote about a while ago now in his experience, something that people have come to call Conway's Law, which in his words was organizations which design systems are constrained to produce designs which are copies of the communication structures of those organizations. And usually, Conway's Law is brought up in a negative sense, like that it's something to be avoided. But I actually kind of wanted to ask a question. When might you want your systems and your organization to mirror each other in some way? Like, would there be value in that? And as kind of an analogy, I wanted to talk about ants for a second. So, if you take an ant colony, these ants manage to coordinate in a number of different activities, whether it's cutting and gathering leaves. These particular kind of ants do some really amazing things, but they do it with essentially no central coordination. At the same time, they have a very rigid structure, but that structure is distributed. And I think we want, as DevOps, to enable exactly this sort of loosely coupled work across teams. That's common tools, common practices, and best practices. And it's probably your job to help deploy those tools and establish those processes. I've heard teams talk about creating a paved road, that is, making an easy way for teams to adopt these kinds of tools and processes, and not necessarily constraining them, but offering the best options for them. So I think, Conway's Law can be a good thing, right? If we want to optimize for velocity, if we want to optimize for fast moving teams, then we want them to be able to make decisions independently of one another. And to do that, they need to build strong abstractions between not only their teams, but their services. So they need to be loosely coupled, right? So I think we should be embracing Conway's Law. We should be shipping our org charts, and we should be thinking about how we can apply the same sorts of constraints around structure, not only to the software, but to our organizations themselves. So, I just grabbed some logos. These are some of my tools, favorite tools that, some of which we use for coordination and orchestration, for building and for deployment. These are all ways that we as DevOps engineers or as SRE can enable teams to do this. And, maybe as a service owner, you're using some of these tools. But here's the thing about all these tools and about this structure, which is your users probably don't care. Your user had an error occur, and okay, sure, but how do we map that back into the software that's actually behind that? Is that part of the client? Is that part of the API gateway, or is that further in one of the other backends? Because you do care about this structure, and you and other people in your organization need to be able to figure out why that error occurred in order to correct it. So I think, in a lot of ways, DevOps and distributed architectures go hand in hand, whether that's microservices or serverless or some other service-oriented architecture. Those architectures all enable a kind of distributed ownership, enable teams to really own their own services end to end. At the same time, there's a lot of great tools out there that automate distributed infrastructure management, whether that's things like Kubernetes or other serverless technologies, but these are all ways that sort of amplify your work as a DevOps engineer. But what about, what do we lose here? Sure, we've created these really strong abstractions, we've built loosely coupled teams, but what about end-to-end visibility? What about understanding what our users are seeing? Is that something that we can solve with metrics? What about not just in our software, but in our organization? How do we communicate across teams? How do we find the right team to communicate to in the middle of an incident? So sort of as a spoiler alert, so here's what I want to kind of talk about in the rest of this presentation. So first of all, how do we recover that visibility that we lost, that end-to-end understanding of our systems with distributed tracing? And I'm actually going to spend a bunch of time talking about how we can do that starting from a single service. So in the end, of course, we want distributed tracing to be about end-to-end observability, but we have to start somewhere, and there's still value to be had in a single service. Second, I want to start with your users and understand what they care about and how that maps into things like service level indicators, and how do we use symptoms to decide when to take action. And finally, once we've decided that we need to take action, how do we connect cause and effect? Whether that's performing root cause analysis when something's on fire, or when we're trying to be a little bit more proactive and maybe trying to plan some performance optimization work. Before I do that, though, I want to give a quick review for those of you that don't know a lot about distributed tracing. I just want to spend a minute or two kind of bringing you up to speed. For everybody else, just hang on for just a second. So tracing is a diagnostic that reveals a couple of things. First, how a set of services coordinate to handle an end user request. Now, by end user requests, I mean all the way from mobile or browser to backends to databases. So it's important that we can understand that at some point end to end. And traces will also include some other important metadata. So that might take the form of logs or tags or other annotations. But the point of all of this is to provide a very request-centric view. So in as much as the architectures that we're choosing enable teams and services to work independently, tracing is a little bit of a foil to that. It allows us to take the opposite perspective and understand it from where our users are seeing things. And just to clarify, there's a bunch of other kinds of tracing. So process tracing, kernel tracing, browser tracing. Those are all great things. Most of them focus on an individual piece of your application. And what I want to talk about today is distributed tracing. We're really looking at the bigger picture. So to be super concrete, so here's a picture of what an individual trace might look like. There's a bunch of tools that'll do this. Some of them look like this. They all kind of look like Gantt charts to me a little bit. So just to kind of like focus on one tool and this one trace. So in this visualization here at the upper left, we have sort of a summary of the request. So it's supposed to be kind of like an inverse flame graph, although there's not a lot of flames in this one, but each of the colors represents a different service. The passage of time goes from left to right, and then we go from top to bottom. We go from the top down to the bottom of the stack. On the lower left, we have sort of a breakout of one part of that trace where now we get to see individual pieces, what services they're associated, what the operations are, how long they're taking. And then on the right-hand side, there's a bunch of other metadata that tells us a little bit more about what's going on inside. So some tags that tell us something about the host that we're running on, maybe what communication protocol. We happen to be using gRPC here. And then we have a log as well. It's associated that there was a deadline set in some part of this. So, so that's kind of what they look like, just to kind of break into the terminology. So the trace, it really represents the end-to-end request. That's a single trace. And a trace consists of maybe one, but maybe thousands of these individual spans. So a span is just the work done, or some of the work done by an individual service as part of this request. And I mean, in the end, what it really is just a timed event and some metadata. So it has some duration associated with it and some additional information that tells us about what happened. So to kind of break out one of those pieces of what we looked at in the previous slide, each of those lines represents a span. And since time was going from left to right, the start was on the left and the finish was on the right. And the other pieces of data here we have are the duration of the span, how long it took to actually do this work, the name of the service that the work was done by, and then what in tracing is called the operation usually. So this is, it could be the endpoint, it could be some just other description of the work that's being done. If you want to understand kind of more of the background on this, go and Google for Dapper. That was a system that was built at Google to do this kind of tracing by one of my co-founders. And they wrote a nice technical report about how they set that up in their experience doing that. It's pretty interesting to kind of see what happened at scale. Okay, so maybe I've answered a few questions, maybe I've raised a few as well. So some things that might be in your mind here, you might be thinking, can I have too many spans? What is enough spans? And what are the right spans among those? I mentioned tracing as this end-to-end thing. I also said we're going to talk about a bunch about how we can get value out of tracing for a single service. So one question might be, where do I start? And do I need all these traces? There's potentially a lot of data here. You might be concerned about overhead. And if we want to pick and choose among these traces, which are the ones that matter? Okay, so with that behind us, I want to talk to you all either as service owners or as the folks that support service owners. So, you're a service owner, you're sort of a cog in this big wheel, maybe just a tooth on this big cog. And I mean, this is, I don't know, you can find a bunch of these things on the internet. Now, Netflix has this one that's kind of insane. I don't really know exactly what to take from this, except for that a service is just one small piece of this bigger thing. And as a service owner, like, what do you really care about? Like, if you are just this one little piece here, I mean, I think you care about, at least to sort of a first order of approximation, your neighbors. Yeah, those are the services that are sort of depending on you and that you're depending on. But this, excuse me, this representation is, well, I don't know, it kind of puts you in the bigger picture, but it doesn't really tell you what to do next. So anyway, with that, I want to ask a couple of questions. As a service owner, who are your users? I hope you know that. And what do they expect from you? How are they going to measure your success? And if you don't hit that, if you don't meet those expectations, what will they do? What will they do if you fail? So one way we can sort of formalize the answers to those questions are through what's called service levels. And this is a little jargony, and often these things will get a little bit confused. That's fine. I don't want to be sort of a service level snob about this, but I think there's some value in being a little bit clear, at least about what the three pieces are. And I'm going to use this terminology since that's what we used when I was at Google, but you can think of it in some other ways if you want to. So first, just to start with service level indicators, or SLIs. This is really just what you measure. And that could be something like latency. It could also be uptime or correctness. There's a lot of different things that you might measure. And from that, you might define an SLO, or a service level objective. Not every SLI has an SLO, but if an SLI is really important, hopefully you have a target, you have a goal that you're trying to meet. So for example, that might be something like keeping P99 latency below 1 second. It might be achieving 99.9% uptime, or it might be 100% correctness. Finally, if we want to go all the way, we might then define a service level agreement. And this is what happens if you miss that objective, if you fail to meet it. And an agreement is really about the consequences. So this is really getting towards what is the thing that your users will expect when you fail to meet it. And that can take the form of a refund or a cancellation. Not all SLOs will have SLAs, but SLAs can be important because they can understand how to drive investment toward SLOs and SLIs. Before I talk about that, I want to just take a quick little tangent here and to talk about high percentiles. I hope everyone understands this, but it's super important, so I just want to really hammer it home. So I just kind of drew a really simple distributed system here. This is maybe you have some document search system. It's fanning out across a bunch of shards. And say that when we think about the services at the very bottom of the stack here, that just to keep things super simple, the average latency is 1 millisecond, but the 99th percentile latency is 1 second. So that means 1% of the traces are 1,000 times slower than the average request. Now, if an end user request, that is something coming from the top of this little picture, hits only one of those bottom services, well, then of course, 1% of those end user requests will also take a second or more. It's pretty easy, I think. But the thing that happens here, which is maybe a little bit subtle, but really important to understand, is as the complexity of handling those requests increases, and just to take an example of that, increases the number of these service instances at the bottom of the stack that have to participate in that request, this 99th percentile is going to have a bigger and bigger impact. So say that it required 100 of these bottom of the stack services to participate in answering one of these search queries. If that's the case, then 63% of end user requests are going to take more than a second. So even though it's only 1% of the requests at the very bottom of the stack, more than half of the requests that the users would see would take more than a second. So this is all just to say that really, as our systems increase in complexity, that the effects of rare behaviors get magnified through that complexity. And so one of the really important reasons to be measuring 99th percentile, not just at the top of the stack, but throughout, is to understand how that's going to be magnified, because it's going to have a big impact as we kind of go up the stack. Great. Okay, so back to our story here. So just to give a concrete example of some service levels. So here's a graph of latency that I stole from our system. So the SLI, the indicator, that is just this measure of latency. Some folks like to scale these so that there's a clear, kind of 0 to 1 range. I left it here just because I think that's the way I think of it. So once we've started measuring that SLI, we can set a goal for ourselves. So that might be something like I mentioned, that we want to keep 99th percentile latency below 1 second. And in terms of the graph, that's going to be something that just shows up here as this straight line. And finally, SLAs don't really appear in the graph itself. That's really a little bit more about the agreement and the contract that we have with our users. And like I said, this isn't going to be something that's necessarily going to affect what alerts you're setting directly, or it might not be something that is something that you think about, in the moment of an outage. But it should really drive how you think about investment, right? So if your SLA is something that does have a refund associated with it, well, you can think about that as a kind of budget that you can now spend, and you can trade off whether or not that's money that you want to give back to your customers or money that you want to spend improving your software. You can also think about the impact on your brand, and even if you're not refunding a customer directly, how is this going to affect the way that people perceive your service and use it? Okay, so some just best practices around choosing performance SLIs. So first of all, setting the right scope is really important. It might be easy just to think about, okay, well, I own a service, so I'm just going to set an SLI for that service. Latency is important for my users, so I'm going to do that. But think for a second about the different kinds of things that your service does. So just to take a super simple example, say that you have two endpoints, one that reads and one that writes. Chances are the read one is going to be a lot faster than the write one. So now when you're going to set a single SLI, if you're going to try to cover both of those, either you're going to set it so wide, it's going to be such a slow SLI, that you're not going to really see or understand performance changes in the faster operation, in the read operation. Or you're going to set it so tight that you're going to constantly be missing your SLO, not because anything's really wrong, but just because writes take longer. So in that case, it might be better to actually set two SLIs, one for your read operation and one for your write operation, so that you can really measure performance in a way that's meaningful for both of them. Once you've chosen the right scope, now it's about choosing the right kinds of performance to measure. And so I think the place where I would start here would be with high percentile latency and error rate. Those are things that many users will care about, and they're great indicators of sort of the overall health of what you're doing. Beyond that, you might also measure something like throughput. It's a little bit harder to set an SLO around this. So this is something like the number of requests that you're satisfying at a given in a given time period, because this can depend on the behavior of your users. But it might be something that you still want to measure just to see if this, to look at trends and to see if it's going up or down quickly. And finally, I threw it on here in parentheses. This is sort of, in my mind, definitely fourth on the list, is looking at saturation. So what percentage of your resources are you utilizing to serve traffic right now? And this is really important for kind of getting ahead of things. So, understanding when you might need to increase the size of a database or scale out to a new set of shards or something like that. I kind of qualified this and I said performance SLIs. Yes, uptime and correctness are also really important, but because we typically achieve those through kind of different means, we end up measuring them in different ways. And a lot of what I wanted to talk about today is really more on the performance side of things. Another way of thinking about what we measure is to kind of make an analogy to medicine. So, when we think about our health and we think about whether or not we are healthy, one of the first things we do is we measure symptoms. And symptoms are things that are easy to observe, but at the same time indicate that something is not, is not the way it should be. So, the easiest example of this are things like measuring body temperature and pulse. Those are super easy to measure, super non-invasive, and they're actually great indicators of other things happening. From a software point of view, these symptoms will usually be pretty related to your SLOs. These are things that your users care about. And luckily, there aren't that many of them. So measuring them and observing them is not particularly hard. The second piece of this is to try to understand the causes of those problems when something has gone wrong. And causes are really things that you can take action to address in some way. If we want to continue the analogy, these are really the diagnoses. And like in medicine, there's typically too many of these to count. So, we don't start by, trying to, look for individual diseases or illnesses. We start with, like I said, body temperature. And likewise, when we're talking about software, we shouldn't really immediately be starting with, is this particular host overloaded? Well, what's really important is, are we serving traffic in a way that meets our users' needs or not? One of the things about choosing symptoms that are easy to observe and a small number of them, hopefully, is that those should really be robust to changes in your software. We want the symptoms to stay pretty stable over time, just so that we don't have to adapt them as quickly as we roll out new versions of our software. The causes, on the other hand, just by sort of definition, are going to change all the time. So another kind of important distinction in this is thinking about how robust or how stable these things are and where they fit in this model. So kind of to sum this up, I think the shortest version of this is just know your users. And users might be your application's end users. It might be other services within your applications. And what those users expect will tell you what things you need to measure. It'll tell you what symptoms matter. And then by extension, what you should be alerting on. Usually these are pretty simple things, like does your service work or not? But it's really important to understand that. I worked at a previous company where we were doing what I kind of think of now as low frequency trading. So it was really replacing a pen and paper process for doing financial trading. And we talk about things like uptime and latency and things like that, but it turned out that this set of users really didn't care about uptime. We were replacing a process that was so slow and so manual that we could have our service down for 5, 10, 20 minutes in the middle of a trading day, and no one would blink an eye. That was just sort of business as usual for them. What did matter for them was correctness and doing the right trades. And that meant for us that we invested a lot in testing and be able to reproduce interesting conditions within the market. We didn't worry quite as much about reliability because that was something that we didn't really need to have an SLA around, and therefore we didn't need to invest in. Okay, we're measuring the right things and something's gone wrong. Not in my slides, just in your service. So when something goes wrong, I think the easiest way to think about this is really thinking about change. Change drives outages. And there's lots of different kinds of changes. So one set of changes is things that are internal to your service. You just rolled something new out, whether that's a new version of the code or a new configuration. And this, is pretty common and is definitely important. I'm not really going to talk that much about this because I think this is something that everyone understands and expects. What I did want to talk about a bunch of external kinds of changes. So that might be your users. Again, it might be end users. It might be just other services within your application. And those users are doing something different. Maybe good, maybe bad, but different from your point of view. Another set of external changes might be the infrastructure itself. You might be competing for resources, with other services or even with yourself. And the last set of external changes are upstream changes. So that might be all of these sorts of things, whether they're new versions, config changes, resource starvation, happening to some of your dependencies. And ultimately, in any of these cases, your goal is to explain that variation in performance, that is the performance of your service in terms of one of these changes, because that'll tell you what you need to do next. So what I wanted to do is sort of walk through a bunch of examples using traces about how we can identify these different kinds of changes. And like I said, I wanted to focus on single service traces. I know we talk a lot about traces as an end-to-end thing, but it really starts with these individual services and understanding the inputs and outputs of those services and how tracing can help map changes in those inputs and outputs and help you understand what actions you need to take next. So users, as operators, sometimes it can be a little hard to empathize with our users, but they are critical to our business. They are our business. Users do lots of really interesting things. Maybe they thought of a new use case, a new way of using your service that you hadn't considered and you hadn't load tested for. And when they do, that has impact on your service. Maybe you just had a viral tweet and there's a lot of people that are coming to use your service that you hadn't expected. That's great. These are all things that you want. You want your users to be engaged. And now the question is just understanding how that affects your service performance. So I wanted to take an example from Lightstep. So like I said, we use Lightstep to monitor Lightstep itself. And this is a piece of a bigger trace. Again, I sort of narrowed it down to one individual service. This is a service that we call live view, and live view does a couple of different things, not only showing live view, but also loading historical data. So let that be a lesson to you when naming services. And the thing that we were observing here is that live view was responsible for a slower page load. So in effect, live view has an SLO to other parts of our service, which it needs to be able to serve these queries within a reasonable period of time that'll support interactive rendering. And 3.65 seconds is too long. It's outside of that. So now we have an example to look at here to understand why things went wrong. And if we kind of look down within the trace, it turns out to be in the processing. So there's sort of, looks like 227 spans below this that contributed to loading and processing these histograms. And we can see, we actually were able to load it pretty fast. It came from storage in 194 milliseconds. And the rest of this time turned out to be in processing the data itself. It didn't turn out to be a thing that makes for a great demo. I'm sure you have all done this sort of manual grepping through logs, looking at a bunch of different metrics, trying to understand the size of the data here. It turned out in all of that, we were able to isolate it to a particular project ID, which for us corresponds basically to one of our customers. And that user was just behaving a little bit differently than a lot of our other customers, and they were seeing much poorer performance than those other customers. And the reason was that they just had much bigger traces. They had a lot of traces that fit within this query, and there was just a lot of processing that was going on here. I'd like to tell a better story for this. This is actually something that happened and that we were looking at back in July of last year, and it really drove us to think about how we could better support this use case. You know, how can we automate this process of grepping through these logs and tracking down all these metrics, really of building these different hypotheses and then trying to map those hypotheses back to the data that we have at hand. And that was something that we were actually able to do. And in the next example, I'll show sort of how we can make this process a lot faster and a lot easier. Okay, so users, we love them. Okay, the second kind of change that can happen here is really at some level, you know, nothing to do with your services themselves. It's just that, you know, isolation isn't perfect. You know, threads still run on CPUs, containers still run on hosts. Maybe we haven't provisioned them exactly the way that we want to. Databases still ultimately have to provide shared access. These are all reasons that, you know, requests can be slow that really have nothing to do with that request itself. So to take another example from Lightstep, this service, sort of more opaquely named Bento, is responsible for managing some metadata within Lightstep. And Bento's SLO says that it needs to be able to serve this metadata pretty fast, actually quite fast, because it's used in serving some other critical traffic, even on our ingress path. And so 1.29 seconds is like way out of SLO for us. And, you know, looking at this portion of the trace, understanding essentially, you know, when did the request come into Bento and when did it go back out? Sort of naively looking at this, we'd say, oh, well, look, you know, of that 1.29 seconds, 1.1, and in fact, you know, almost the whole thing was actually in terms of getting data from a SQL database. So, you know, maybe we need a new index here, or maybe there's some other writer that's misbehaving in terms of this table, and you know, we need to figure out how we can isolate the readers and writers a little bit better. So maybe we need to build a cache or something like that. So yeah, so let's try and understand what's happening here. And really, the goal here would be to try to understand what makes these requests different, right? So obviously, most of them are not taking this long. This is an outlier in a lot of ways, but still important to understand those, you know, kind of as per what I was saying about, you know, even 1% at the bottom of the stack can have a much bigger impact higher up. Okay, so to understand what's different, you know, what you can do is not just look at a single trace, but look at a collection of traces and try to understand what makes that set, what defines that set, and what distinguishes different parts of that set. So to do that, and a way to kind of visualize that is to look not just at a single trace, but at this histogram, a latency histogram describing the latency of a set of these traces. So just to kind of go through the pieces of this. So this histogram shows the latency, the duration. So the vertical axis here is how long it took to, the horizontal axis here is how long it took to process an individual request. And the vertical axis is the number of instances that were that fast or that slow. So over on the left-hand side here are the faster requests. We can see a bunch of requests within Bento here take on the order of a millisecond. But there are some that are quite a bit slower that take as much as a second to process, like the example that we were just looking at. And like I said, they are rare, but there are, you know, a bunch of them that are out there, you know, on the order of, you know, within this sample of 100,000 spans, you know, there are thousands of them that are out there. So definitely, you know, even, you know, the 95th percentile is somewhere kind of on the order of a couple hundred milliseconds. So it's still 2 orders of magnitude faster, slower than the fastest one. So, okay, what we want to do now is understand within this population what makes the slow ones slow and what makes them different than the fast ones. So, well, we can just ask that question essentially. So we can do an automated analysis where we look at different characteristics of these spans and of the traces that they're part of. And we can ask what makes the ones on the left, on the right, different from the ones on the left. And the answer here is actually not the database in the end. I mean, that sort of makes sense from one point of view. This is metadata. It's not stuff that changes that often. So we really shouldn't have another like a fast writer that's contending. It's really pretty simple. Like the idea that we need an index is actually a little bit far-fetched. What we actually found was that this was actually contention for CPU on the host that Bento was running on. So we have a tag here that describes the host. And this number here, 0.63, is an indication of how strong the correlation is between the occurrence of this tag and the traces being in this slow subset. So again, what we were able to do in this case, kind of unlike the previous one, is by looking at a bunch of traces in an automated fashion, we can immediately find maybe what a hypothesis, and we can try to validate that hypothesis that wasn't what we as humans might have thought of. Even as experienced engineers, our intuition can often be wrong about what's going on here. And in this case, we're actually able to go to another tool and verify that, in fact, this particular host was overloaded. Partly because of some other work that Bento was doing, partly because of some other things that were happening, and that explained what was going on here. I think to kind of go one step beyond P99 latency and other high percentile latency, like I was talking about before, really the shape here is really important. You can see there's a bunch of different behaviors that are present within Bento. Each of these different sort of bumps within the histogram could represent a different problem, a different opportunity for optimization. And I'm not going to get any more into that, but if you're interested, search for performance as a shape. We've got another talk on devops.com to talk about how you can think of performance not just as a single number, but really as a much richer set of behaviors, and try to understand how that can help you better understand your service. Okay, the last sort of change that I wanted to talk about is upstream services. So these are your services dependencies, things that you depend on in order to provide service, and understanding their performance is really critical in understanding how it impacts yours. So I want to take one more example from Lightstep here. This is from a service that we call the trace assembler, pretty important to our business overall, as it turns out. And the thing that was happening here is that trace assembler is responsible for a bunch of different things. This particular operation where it stores trace data durably, and this is not quite as apparent to our users in the sense that this is not something that's part of an interactive request, but it's still important to understand. If we're keeping up, we're recording billions and billions of traces. I think last year we recorded over 10 billion traces. So just keeping up with that rate means that we need to be doing it at a pretty good clip. And 7 seconds is pretty long for one of those things. So looking at this trace, we're able to understand sort of okay, our SLIs is definitely degraded here. And if we look at what the problem is, the data was actually being stored in two different ways. Part of it was being stored in Google Cloud Storage, part of it being stored in Spanner. And I don't want to pick on Google Cloud or anything, like everyone has issues at times, but for us it was really important to understand, first of all, this is nothing in our code, so it's not something that we wasn't a bad push or something like that. It wasn't any change in the behavior of our users. It wasn't something where they were suddenly sending us more data or we were assembling more traces for them. It was really about one of our upstream dependencies. And even among those, it was important to understand which of those different storage systems it was. So now we can really, take the right actions to mitigate this problem. Whether that's, moving to a different region, whether that's throttling this in some way, moving to some other storage mechanism temporarily. Those are all, possible actions that we can take. But, knowing that which of the actions those would be is really important, and we don't go off in some wild goose chase and try and figure out, maybe we push some bad code or something like that. So I guess to kind of review all of this, so unexpected user behavior can lead to slow responses, contending for resources can lead to slow responses, waiting for upstream services can lead to slow responses. And all this kind of makes, I don't want to be a downer or anything, but it's like some of my colleagues at within the SRE organization used to say, hope is not a strategy, and we need to be prepared for these things, and we need to be able to understand which of these situations we're in order for us to take the right response and get things back on track quickly. One other quick kind of side note on this, I think we can think a little bit about how to instrument based upon these different kinds of changes. In particular, sort of what's the right granularity of spans? Should we have one span for each user request as it passes through, 2 or 100, and even within those spans, what are the right tags? And there's some simple guidelines that we can kind of take away from these kinds of examples. So for ingress operations, that is where we're serving some of our users, understanding the peer, where is this coming from, important request info, Maybe that would be something about the customer. It might be something about the segment that they're in. It could be what geographic location they're coming from. And then something about the response code is also really important. Did we think of this as a successful response or not? For egress operations, that is, for our upstream dependencies, a kind of similar set of things, not only important parts of our requests, but important parts of the response, not only the response code, like was this a success or a failure, but how big was this response? Was this a query that returned no results or a million? And then, within a particular service, looking at large components or libraries. And often there'll be pretty domain-specific tags for this kind of thing. But, we were doing some significant processing of these histograms within the LiveView service, and that sort of warranted its own set of spans. Generally, all of these and any other place where failure is likely and where performance might be unpredictable. The idea of these spans is really these are going to be signals that will help us figure out what's going on later. And obviously having too many is going to increase the cost of doing distributed tracing. So focusing on the cases where failure is likely is important, and having the right sort of tags there to do the kinds of correlation analysis that I described that we were doing for Bento. The other question you might have is like, well, why not just more dashboards, right? Why can't we just measure more of these things, for each of these different SLIs that we care about, for each of our different upstream services, for each of these different large components that we have internally. And like I was saying, your goal is really to explain that variation in performance. Doing so is not just enumerating all of these things, because there's going to be hundreds or thousands of them. And as the complexity of your system increases, there's going to just be more and more of those things. What's really important for you to do that effectively is to be able to quickly identify the metrics that matter. And that's really where I think that tracing is important, because it ties these different tags and these different performance characteristics back to your SLIs, right? So tracing enables you to see how your users' actions are impacting your SLI, how your resource contention might be affecting that SLI, and finally, how the services you depend on might also be affecting your SLI. So all of this was sort of, kind of thinking about these more reactive situations. And the other thing that we might want to do is step back a little bit and think about how we can look at the bigger picture, try to see a little bit farther away, and see if we can be a little bit more proactive in how we're approaching our work, and how we can do that with distributed tracing. So the first and really important step here is to establish a ground truth for what's happening in production. And once we do that, step 2, make it better, I guess step 3, profit. But really, I want to focus on step 1. Like, we can do testing. Testing is important. We can do load testing. We can try and, we can look in our QA environments. But understanding what's happening in production, what our real users are seeing, that's really what should be driving any proactive work. And that could be, thinking about how you're planning performance optimizations. Say you've got some time set aside for the next couple of weeks to improve performance. Maybe that's a company-wide initiative. Or it could be that you're thinking about bringing on a new SaaS provider and you're trying to evaluate them. Really understanding performance in production is important for both of these situations. So I want to go through a couple examples. So here's a picture, maybe a little bit smaller, of what your service might look like. This is sort of a demo service that we show. And really, if we're trying to improve end user performance, we need to look at it sort of from this holistic point of view. To kind of give a sense why I want to look at Amdahl's law. So Amdahl's law is usually brought up in the context of parallel computing. But really what Amdahl's law is about, how optimization in parts of a bigger task can impact the performance of that bigger task. So just to take a super simple example, say that we've got this work here to do. Again, sort of think of the time passing sort of from left to right here, and we can break this task down into these 2 pieces. On the left, say service A is doing some work, and then on the right, service B is doing some work. And this kind of, might seem a little bit obvious, but if we improve service A, it's not really going to matter that much. On the other hand, if we can improve service B by kind of the same proportion, that'll have a really big impact. So given a choice between speeding up A and B, a 50% improvement in B is going to have a way bigger impact than a 50% improvement in A. And the other thing that Amdahl's law will tell us is that no improvement in A will ever improve overall performance by more than 15%. So if we're looking for a big win, even if we could wave a magic wand and make service A's work become instantaneous, that's still only going to be a 15% improvement. And like I said, this is all kind of obvious once you have the data. But the thing that I've seen happen again and again is we have, say, an organization-wide initiative to improve performance. Service A goes off and says, hey, we're going to work on this. This is really important. Likewise, Service B says, we're going to work on this. This is really important. Really, Service A should probably be spending their time on something else because they're not going to have a big impact on what the company's overall performance is going to be. If you kind of see this in a trace, so here's, this is a contrived example where we have sort of a charger, but the point is here that there's sort of two pieces to charging a customer. First, we want to do some sort of fraud check to make sure that they're sort of on the up and up. And then secondly, we're actually going to go and process the transaction through an external payment gateway. And the point, what Amdahl's law is going to tell us here is that really improving database performance here is not going to change things very much. If we're going to spend time on this, we really need to think about how we can improve performance of what the gateway is doing. That's what's going to have an impact on our users. So kind of a recipe for doing meaningful performance improvements. So first, choose the thing that you're actually trying to improve. I said latency, but really it's got to be a lot more specific than that. Maybe you're talking about, 50th percentile latency, sort of median case, great. So choose that. Maybe you're just worried about P99 latency. Maybe there's other things, but really be super precise in what you're really trying to improve. And then second, collect a bunch of traces within that population. Like I said, being specific is critical. We need to, if we're going to try and improve P99 latency, we just need to look at the 1% of traces that are the slowest. And then what we want to do is just get enough traces within that sample to have a sort of a meaningful set that we can then draw some conclusions from. And then what we do is we just find the biggest contributors to the aggregate critical path. So we take the traces in that sample and we just kind of put them end to end. So if we sort of imagine my simple example with these two different pieces, Service A and Service B, it turns out Service A is usually shorter, Service B is usually longer. And we just take these requests and we kind of put them end to end and look at that whole thing and then just ask the question, how much faster could it be if we improved A? How much faster could that be if we improved B? Second example I want to talk about is SAS. And thinking about SAS just as another service. So SAS is a great option for a lot of things. We use SAS for a lot of things at Lightstep. It's a way for us to focus on the places where we as an engineering team can provide the most value and make the operational concerns someone else's problem. So storage, analysis, load balancing, there's a lot of great places where we can just push that work on someone else. That's great. The other place where you might want to consider this is if you want to offload some particularly complex or tricky functionality, especially where there's things like compliance involved. So pushing off payments, things around fraud and abuse detection or authentication, stuff that's really tricky to get right. But all of that said, really can and should treat SAS just like any other service. And that means starting in just like, if you were going to bring up a new service within your application, thinking about performance during design and sort of prototyping and evaluation phase, same thing is true for SAS. So, I'm not a lawyer, but I do read these SLAs, and, this is what SLAs look like. This is just sort of the way the industry works. But, when I'm designing a system, this doesn't really tell me that much. Okay, so, downtime for less than a minute doesn't really count. I know that's what everybody does, but a minute is a long time. And if this is going to be on an interactive request path, it's got to be a lot faster than that. And so these SLAs really don't give you the visibility that you need when you're doing this evaluation. And, often they really just focus on uptime and correctness, but you need to understand latency too. So we actually did this as part of evaluating SAS at some point at Lightstep. So part of what Lightstep does in addition to storing traces is we store some time series data. And we were evaluating a couple of different options. One of them was to run Cassandra locally. This is sort of low frequency time series, so it doesn't demand super high ingress. And so, we did some benchmarking of Cassandra and we looked at latency across a different spectrum. So on this graph, these 3 lines, there's actually 4, but it's a little bit hard to see, represent these 4 different percentiles. So for this read operation on Cassandra, the P50 latency was about 2 milliseconds. And then you can see that's sort of the flat line, that's right next to 0. And then there's a kind of purple, blue, and light blue lines above that that represent P95, P99, and P99.9 latency. And what we want to do is actually compare this against, we're looking at a SAS solution, and so we compared this against Spanner. And Spanner's graph looks pretty different. I can kind of put these side by side. But it was pretty interesting to see some of the performance characteristics that were different. So one thing is that the median latency on Spanner is actually quite a bit higher. It's about more than 3 times higher. But at the same time, the long tail latency is way, way tighter on Spanner. And this was pretty interesting for us to see, and pretty interesting to think about how this would work, if, like I said, this 1% of requests is at the bottom of the stack, how that's going to bubble back up higher in our own stack. So, I mean, the takeaway in this is just, SAS is just like anything else. Measure it like any other service you would have. If it's upstream to you, it matters. And you should be using best practices for things like provisioning, understanding what you need from it. You want to instrument, even if you can't instrument the SAS itself, instrumenting the client libraries or the requests you're making to it, and monitor it just like you would any of your other downstream dependencies. Okay, sort of with that, like I said, I think DevOps and distributed systems is a great match. The software architecture, behind things like microservices and serverless is a great way to enable distributed ownership. And there's a lot of great tools in this space that help really amplify the work that DevOps does. At the same time, distributed tracing is a great way to regain that end-to-end visibility. I talked a lot about single services and the visibility you can get just from mapping a single input to an output. But really, distributed tracing is a way to sort of automate organizational navigation. It tells you who you need to talk to when something is going wrong. And like I said, it helps you connect those inputs to outputs in a way that matters. So understanding, how your upstream dependencies are actually affecting your users. Finally, I just want to leave you with this cheat sheet. So first of all, and most importantly, know what your users care about, whether that's latency, errors, uptime, whatever it is. Know it, measure it, and alert on it. And then be able to connect that variation and those service level indicators back to root causes with tracing. Understanding whether that's user behavior that's changed, whether it's upstream services, whether it's SAS performance, whether it's some other contention. And that's either in the case where you're responding to an incident or whether you're trying to get ahead of things and improve baseline performance. And finally, I think a thing that sort of came up a couple of times is we think about tracing not just as looking at individual traces. Tracing is really about using the data that's found in tracing to draw conclusions, to form and validate hypotheses. And a lot of times, understanding what's normal and not normal is critical in understanding things, like in the example of an overloaded host. And a lot of times those patterns will only emerge through meaningful samples. So looking at an individual trace might be sort of a one-off case. And by looking at a group of them, we can really take more direct corrective action. And with that, thanks for your attention. I'm happy to take some questions.
Okay, great. We have a few questions in. There is time though, guys, if you have a question for Spoons, go ahead and use your GoToWebinar control panel and submit. I think we have time for 2 or maybe even 3 questions, so let's dive right on in. First question, distributed tracing provides the span time, which is basically time spent. So how do we find the breakdown of the span time?
Yeah, that's a great question. So the way that we would typically recommend do this is essentially building subspans. So you can think of spans within a trace having a kind of parent and child relationship, where the parent is sort of a top level span and the children are sort of the subtasks within that. And like I sort of alluded to, what I would really recommend is looking for what are the big units of maybe unpredictable work or the big places where you might see failure. So that would be in other RPC calls. It could be calls to big libraries that are doing a lot of work. You can also think about doing some analysis of the tags and logs itself within the spans. That's not something I've seen a lot done in tracing, but there's a lot of data there that you can really mine to understand what's happening and within the span itself.
All right, great. Let's see. The next question is. So when do I use tracing and when do I use metrics?
Yeah, that's a great question. I mean, those two, along with logs, are sort of touted as the 3 quote pillars of observability. And that's great, but I think the thing where that's kind of taken people to is they think of these as three separate tools, as discrete units that are sort of holding up the roof, I guess. And really the way that I think that I've come to think of them is not as three separate tools, but as just three sources of data. In as much as like traces are really about the connections between different services, metrics are just about measuring these usually scalar values, and logs are about sort of capturing detailed data about discrete events. But the way that you use those really doesn't require that they're separate things. So you can take trace data and derive metrics from it. Likewise, you can take logs and derive metrics from it. You can use metrics as a way of explaining what's happening during a trace. So the way that I would think of it is more about sort of the use cases. You want to sort of be able to, when you're thinking about instrumentation and generating the data itself, really just think about like what are the important kind of key measurements that'll help you understand what the symptoms are and the current performance of those systems, and how what kinds of causes you might need to use to explain that variation. And then in terms of whether you're using a metrics tool or a tracing tool, that's sort of kind of an after the fact decision that you can make, and even changes over time as you might pick different tools and learn about new functionality.
Okay, great. I think we have time for one more question. Let's see, we just got this one in. What about finding out where in the code that comprises a microservices time is being spent?
Yeah, so I think if I understand the question, sort of mapping from a span back to the code itself, that's something, when we think about instrumentation in tracing, it's often a fairly manual process, but one of the things that we at Lightstep and others are doing through projects like Open Tracing is to try and automate that in some way. And the way that that automation can occur in a more sort of platform or language specific way would be to actually, annotate traces with stack traces, so you can see within a process what's happening, and even annotating spans with the lines of code where those things start. And then you can link from a trace right back into your version control system, your source code repository, and understand where those things are. We also see and recommend tagging spans with releases and versions of the software, so that you can be sure that you're looking at the right code to understand that performance.
All right. Great. Well, we're just a few minutes to the top of the hour, so unfortunately that is all the time that we have for the question and answer period. If we didn't get to your question, I am very sorry, but please know that the folks at Lightstep will be getting a copy of all of the questions that came through, so I'm sure somebody from their organization will be more than happy to follow up with you offline. I also want to remind the audience that today's event has been recorded, so if you missed any or all of it, or if you just want to listen to it again, you will have the opportunity. We'll be sending out an email later on today that includes a link to access the webinar on demand. The webinar is also going to be living on the DevOps.com website, so you can always find it there. Just go to www.devops.com/webinars, look in the on demand section, and it should be right there waiting for you. And while you're there, please take a look at the other webinars that we have, both upcoming and on demand. Hopefully there'll be one or two there that pique your interest. Spoons, thanks for a great presentation. Appreciate
my pleasure.
Yeah, anytime. And I also want to thank the audience for joining me today. This is Charlene O'Hanlon, and I am signing off. Have a great day, everybody.